So we're looking at properties of light, and we've discussed the reflection law. Another thing that light, and indeed all waves do, is refract. Now, what does refraction mean? Well, when waves pass from one medium, which means a material, to another, their speed changes. And because their speed changes, they bend. So first of all, why does the speed change? Well, water waves, for instance, travel faster in deeper water, and they start to slow down when the water gets shallow. That's why they break, right? The bottom of the wave slows down, and then the top of the wave overtakes it. And largely that's an interaction with the bottom. Little water molecules are doing little circular wavefronts, and when they start to experience some drag from the bottom, they slow down. Sound travels faster in more dense material because when the atoms and molecules are closer together, they pass on that vibration a little more quickly, as it says over here. For light, it actually travels faster in a vacuum, and then as the material becomes more optically dense, that actually slows down the propagation of the light wave simply because the electrons and protons in the material take a little while to respond, or respond rather, to the electromagnetic wave, and that actually slows down the speed at which the electric and magnetic field can be created in space, and so it slows down the propagation of the wave. So let's look at a wavefront here, and it's moving, and it's going to cross from one material into another. Okay, so here's the direction of wave travel, and here's the first material, and then over here's the second material, and we're going to imagine that the wave is traveling more slowly in this second material. So what happens is when this wavefront passes into the material on an angle, you'll see that this particle is going to enter this second material, and it's going to slow down. So instead of being up here with the other parts of the wave, it's not going to have traveled as far. Say it's only traveled to here, and so on. These other points have also fallen behind where the wavefront, and so the wavefront is now sort of tilted. It's sort of on an angle where this part of the wavefront has traveled less distance because it's going more slowly. So now, as the wave travels through space, even more of it has entered the slow material, so even more of it is following behind. The part that's been in the second material for the longest amount of time has fallen behind the most, and then the bits of it that have just entered this second material have fallen down the wavefront only by a little bit. So what you see then is that the wave in the second material is now traveling in a different direction. So the bending is due to the slowing down. Now, obviously, we're not losing any waves here, so we've got the same number of waves per second in the first material that we did in the second. So the frequency is the same. But notice that these waves are a lot closer together, so the wavelength is smaller. So not only is the speed smaller, but so is the wavelength. So if we say, call this material 1, and then I'll use like speed 1, wavelength 1, and frequency 1, and then over here we've got speed 2, wavelength 2, and frequency 2, we can say that V1 was faster and V2 was slower. Wavelength 2 got smaller. But we weren't losing any waves. We had the same number of waves per second in material 1 and material 2. Now, if we use the wave equation, lambda f is v, then we know a speed is, a frequency rather, is a v over a lambda. So if f1 is f2, we can conclude that v1 over lambda 1 must be v2 over lambda 2, and then we rearrange that and say v1 over v2 is lambda 1 over lambda 2. And so this is the law of refraction so far. Now, because V2 got slower. This was a smaller number. And I think I actually want to do this the other way around, don't I? Let's see. I want the ones in the top. No, that's correct. Okay, good. So because V2 got slower, that means this number is bigger than 1, lambda 2 must also get smaller. So that this ratio is also larger than 1. Now, on speed, the speed depends on the material in some way. And we're going to define, first of all, just a reminder, light speed, 3 times 10 to the 8 meters per second. We're going to define something that relates to the material. It's known as the index of refraction for the material. And it's a speed slowdown factor for light traveling through that material. It's a ratio of c over v. That's the index of refraction. Now, c is how fast light goes in a vacuum. V stands for the speed of light in that material. Now, if we rearrange that a little bit, n is c over v, and solve it for v, we get v is c over n. And so you could see, indeed, that n is a slowdown factor. It's by what factor does light slow down in that material. So for instance, for air, n is about 1. It's really close to 1. So that means that light isn't slowing down very much as it moves through air as compared with its ideal speed in a vacuum. Right? It's just a tiny bit less. By contrast, in glass, the index of refraction is about 1.5. So that means that the speed of light in glass has slowed down from 3 times 10 to the 8 meters per second, its vacuum speed, down to a speed of 2 times 10 to the 8 meters per second. So we see that the speed is inversely proportional to this index of refraction. And so now we're going to introduce that into our refraction law, which we had previously just cast in terms of speeds and wavelengths. So because speed is inversely proportional to the index of refraction, when n is big, v is small, we're going to write this. Well, I suppose we could just derive it as follows, right? V is c over n1. That would be the speed in the first material. This will be c over n2. And then if we simplify the fractions, we're going to get n2 over n1. Notice that those indices are reversed. That makes sense because speed is inversely proportional to n. So this is what we've got then for our refraction law so far, okay? So basically speed is proportional to wavelength, and they're both inversely proportional to the index of refraction. So if the index of refraction is high, say for a light wave entering glass, then your speed is going to slow down and your wavelength is going to get smaller. That's what these three ratios say. Now, we said that the light wave was going to bend. We'd like to include that in our refraction law. So we're going to do a little derivation here. So we're going to blow up that place where these wave crests were passing from one material into another. So here was the wavefront on the fast side. This was the wavefront on the slow side. Now we're going to add a few more lines here. So here is the part of the wavefront there. And then we're going to say, and then here I'll make, I don't know why I'm putting this one here, but okay, there it is. We're going to realize that the distance between these wave crests is the wavelength. So this was material 1, so this length right here, this is lambda 1. We're going to have to write neatly here. So that's the wavelength in the first material. So that means the distance between these, the perpendicular distance between these wavefronts in this material over here, that is the second wavelength, lambda 2. Now we see that we've got a couple of triangles here, and they're both right triangles because the wavelength must be measured perpendicular. It's perpendicular distance between those wavefronts. So that's 90 degrees. So that means this is a shared hypotenuse. Now, we measure the angles from the imaginary normal line. So this is the angle 2, if you like. Okay, the angle in the second material. And this, way out here, this will be the angle in the first material, or in here, to be a bit more precise, this will be theta 1. Now, I don't really have room there, so I'll write it up here. Theta 1 is this angle right here. Now, that means this is complementary to theta 1. That means this angle down here is also theta 1. So this shared side, this hypotenuse, right? So we can say the sine of theta 1 is lambda 1 over that hypotenuse. Let's write it that way. Sine of angle theta 1 is lambda 1 over hypotenuse. Now we're just going to rearrange that and solve for that shared side, that hypotenuse. We see it is lambda 1 over sine of theta 1. So putting this in the form that we already have for the other ratios, we see that the wavelength is proportional to the sine of the angle, and sine increases with angle. If you look at a graph of sine theta, it goes like this. So a larger sine theta also means a bigger theta. So putting it all together then, oh, and I guess, sorry, that was supposed to go in here, we find Snell's law, which says that the wavelength is proportional to the speed, is proportional to the angle, is inversely proportional to the index of refraction. So these are all proportional to each other and inversely proportional to the index of refraction. Now, you may have done Snell's law in your very first introductory physics 11 course, and usually we just say n1 sine theta 1 is n2 sine theta 2. So this version you're probably familiar with, but adding in these other ratios completes it and gives us the full picture of what's going on when a wave passes from one material into another. Let's do a simple and quick example. So we have a wavelength of 600 nanometers. Nano is 10 to the minus 9. It's traveling in air, so the first material 1.00. I think the next digit might be 3. And then it hits a block of glass. Okay, so let's roughly, sketch that here. There's glass. Here's the normal line. It's got an angle of incidence of 20 degrees. So that will be the angle in the air, right? And we're calling that theta 1. Okay, so here we go. Theta 1. And that is 20 degrees. So we're going to apply Snell's law here. So we've got that written out here. Wavelength is proportional to speed, is proportional to the angle, is inversely proportional to the index of refraction. The speed in the first material, remember V is C over N, and because the index of refraction of air is basically 1, then that means that light's traveling at 3 times 10 to the 8 meters per second in this material. So if we want to find the speed and wavelength of the light in glass, that means speed v2 and wavelength lambda 2. So solving for v2, we cross multiply up, and v2 is n1 v1 over n2. Alternatively, we could just say v2 is c over n2. That would be another way of doing it. But using the ratios, it's 1 over 1.5 times 3 times 10 to the 8, which is exactly what you would get over here. And so again, that's 2 times 10 to the 8 meters per second speed. For the second wavelength, cross multiplying again, lambda 2 is going to be n1 lambda 1 over n2. And so that's 1, and the wavelength was 600 nanometers. And then we divide that by 1.5, and so that is that 400 nanometers? Yes, that's 400 nanometers of wavelength. Alternatively, because the speed slowed down by a factor of 1.5, the wavelength was reduced by a factor of 1.5. Okay, so draw the incident, reflected, and refracted rays roughly to scale. Well, the law of reflection tells us, of course, that the angle of incidence equals the angle of reflection, and there will be some reflection off that surface. So roughly to scale, there it is, same angle on both sides. For the refracted ray, because we're entering a more dense material and the speed is slowing down, right? Speed is proportional to angle, smaller speed, smaller angle. So the angle over on this side will be smaller, i.e. the ray will be closer to the normal. Now let's calculate what that angle is. And so if we start with our relationship here and rearrange a little bit, we get n1 sine theta 1 is n2 sine of theta 2, so it was 1.0 for air, I guess. 20 degrees incident angle. This is 1.5. We want to find theta 2. I suppose we could have done it algebraically as well. This is kind of a very elementary way of doing it, but it still works. And then we've got to, we've got to do the arc sine of this. Squeeze that over a little bit. So arc sine or inverse sine of this quantity, that will be our angle. So we've got to do 2 sine divide by 1.5, and then do the inverse sine. And so you see it's 13.2 degrees. Indeed, as predicted, smaller on this side than it was traveling here in the air. Okay, so that's a basic reminder of Snell's law and perhaps a slightly more sophisticated formulation of it than you are used to. There's another example for you to try here. Give this a whack on your own, stop the video, and then turn the video on and see how you did. Okay, so set it up. So the ray was started off in water, so that's the first material, N1, at an angle of 35 degrees. That's theta 1. Here's theta 2 out in air, N is 1.0. So because the material got less dense, it's actually traveling faster here. And with a larger speed, you'll have a larger wavelength and a larger angle. Then you do the algebra, you find it's up to about 50 degrees. Okay, so hopefully you got that right. And now we'll continue on and we'll talk about an interesting phenomenon known as total internal reflection. Okay, so we want to demonstrate the phenomenon of total internal reflection here. We've got light from a ray box, which is traveling into a glass wedge and then emerging here into the air. So the air on this side is less dense than the glass on this side. So we just want to vary the angle of incidence here from the ray box. Now we can see that the angle of incidence here inside the glass is smaller than the angle of refraction in the air. So we've got an angle there of about 30 degrees in the glass, and then over here in the air it's about 50 degrees. So the angle of incidence is clearly smaller than the angle of refraction. As we increase the angle of incidence further, we can see that the light ray, the angle of refraction measured from the imaginary normal line over here, is getting closer and closer to 90 degrees. And we'll reach a certain point where the ray essentially is about to disappear. So right now the angle of refraction is 90 degrees. Measured from this imaginary normal, we've got a 90-degree angle there. We also see interesting effects there where the light is actually being split up into its constituent colors. That's a phenomenon known as dispersion, and there's a slightly different index of refraction for red light than there is for blue light. We also notice over here that the reflection line has gotten quite strong. That's simply because most of the wave energy is now being reflected and very little is being transmitted onto the other side. If we increase the angle of incidence just a little bit more, the refracted ray totally disappears, and now all of the light is internally reflected inside the glass. So we're shooting light at a transparent boundary, and most of it is bouncing back. Virtually all of it is bouncing back. That's total internal reflection. We can demonstrate that over here as well. Here we have just a little tank filled with water, and we've got a laser that will shine into the water here. So here you can see the angle of incidence. It's about 20 degrees from the normal, 25 degrees from the normal in the water, and it's about 50 degrees out in the air. So once again, the angle of refraction is greater than the angle of incidence. As I increase the angle of incidence, notice that the laser light, the refracted ray, is now at about a 60-degree angle, and I'll increase it still further, and now we're up about 70 degrees. And right around here in the mid-40s, once again, the refracted ray totally disappears and all the energy is reflected. That's total internal reflection. So this is light coming from water, hitting the transparent surface of the water, and all of it is bouncing back. There's no refracted wave at this point. That's total internal reflection. Okay, so let's study this mathematically. When light goes from a less dense substance, say like air, into glass, then it bends towards the normal. So if this ray is here in the air, then when it goes into the glass, it will have a smaller angle of incidence. It'll be smaller than the angle will be smaller than it was in the air. So we measure angles with respect to an imaginary normal line. Here's that imaginary normal line here. And so this substance here is air, and then this substance down here is glass. So the angle in the air is larger than the angle in the glass. It bends towards the normal line. Now, if we reverse that experiment, so now we're sending a ray from the glass out into the air, what we find there is that the angle actually increases. It bends away from the normal line. And the normal line, again, is just this imaginary line perpendicular to the interface. So the light ray bends away from the normal line when it's going from something more dense to something less dense. Now, clearly, the angle of refraction can only get to 90 degrees. So in that experiment we just did, if we're going from something that is more dense to something that is less dense, we'll reach a point where our light ray in the glass is now bending and going along the interface in the air. And that is something known as the critical angle. Because if we increase this angle even a little bit more, this refracted ray will totally disappear. So right now it's 90 degrees. This is in the less dense medium air. This is in the more dense medium glass. And this is the critical angle. And if we increase any more the angle of incidence, this ray will totally disappear. And then all of the wave energy will be reflected. Now, I didn't draw the reflected ray here. Let's just add it in. It's relatively faint until you reach this condition here of total internal reflection. Now, of course, by the reflection law, the angle of incidence should equal the angle of reflection. So just let me draw that one. This will also be theta critical. And you really start to notice an increase in the intensity of the reflection as you get close to the critical angle. And beyond the critical angle, you do have total internal reflection. And this, of course, is the principle of fiber optics, where you shoot light down a glass fiber and it stays inside the glass fiber. Let us derive an expression then for the critical angle for water, assuming that the light ray is heading out into air. Okay, so here's the imaginary normal line, and then we're shooting a ray of light here from inside the water, and this is our angle of incidence theta 1, and this is water. And then at the critical angle, we're about to lose our refracted ray. Our angle outside here is 90 degrees. So we apply Snell's law, which says N1, sorry, the way we write it is a little different from that. Let me clean that up. The way we wrote it in class was to say that speed was larger when wavelength was larger, when angle was larger, and that happens when n is smaller. So speed and wavelength are in proportion to angle and inversely in proportional to the index of refraction. So if we rearrange that, then we could say that n1 sine theta 1 is n2 sine theta 2. So this is actually in the water. This is the incident ray in the water, and then this is the refracted ray in air. The index of refraction for water is 1.33, and it's this angle that we're looking for. The index of refraction in air is 1, and at the critical angle, the angle of refraction is 90 degrees. So we solve. Sine of 90 is 1, and then the critical angle in water will just be the inverse sine of 1 divided by 1.33, and then we will do the inverse sine, and we see that's 48.8 degrees. And that's about what we saw in our demonstration. Remember, somewhere in the mid-40s to almost 50, we were losing our refracted ray, and we were seeing total internal reflection.